All right. So what we did not complete last time was these three things: Adam, BFGS, and LBFGS, and I think Newton's method, and it's not written here. So these are the parts in optimization that we were not able to complete last week. So I'll take a few minutes today to complete that, and I think this will be a very short lecture. We'll just go through those portions. So gradient descent is something that we are all familiar with. Given this kind of a convex function, we know that small steps can be taken based on some kind of a predefined learning rate, and we'll be able to get to the optimal set of parameters, which is our minima. And convex functions are such that the global and local minimas are the same thing. So gradient descent will give us a very good set of parameters. But generally, the problem with CNNs is that the loss landscape is not convex. It's something that you see over here. And last time, I think I mentioned this before. The easiest way to see that neural networks are not convex is just by permuting the different neurons. By taking the first neuron and putting it into the second neuron, right? The W1 becomes W2 and so on. You're essentially changing the structure of the neural network itself, but you'll still get the same loss function. So that means that two loss functions have the same loss function has two separate parameter sets. And this makes it like a concave, not a concave, but a non-convex function. So there are other issues in optimization, which is noisy gradient estimation, saddle points, and ill-conditioned noise function. So this is the very simple kind of a gradient descent given Wt, which is our current estimate of our parameters. Our next estimate is going to be based on subtracting some kind of a learning rate alpha multiplied by the gradient, which is dou L by dou W. Very simple, straightforward thing. But whenever we have these kind of concave these local convex local points which are not the global minimum, it's very hard to come out of them. Then there are other cases where we have saddle points where orthogonal directions disagree. So wherever you have your maximum, the opposite of that is not the minimum, right? In this case, it's very clear that you're maximizing in this direction. You can hopefully see my cursor. You're maximizing in this direction while the minimum is the opposite. And that's how you can say that the negative of the gradient is the minimum. But in saddle points, that is not the case. You really don't know where your maximum and minimum are. They are orthogonal sometimes. So gradient descent sometimes gets stuck in this point, and this is where you have to change the way you optimize. And momentum was the first thing that we saw. The intuition of momentum is given here basically, where if you imagine a ball that is rolling downwards, you're not taking the optimization at every point separately. You need to look at how fast it was optimizing in the previous iteration, let's say, and use that in order to update your weights in the next iteration. So that's where we have this terminology called VFT. Before, what we had was Wt plus 1 equals Wt minus alpha into the gradient at that particular iteration. But now it's a Vft plus 1, which is a combination of the gradient at this iteration, which is dou Lf dou W, plus some kind of a velocity function, momentum, which is beta into V of t. Right? So whenever you're stuck in a local minima or saddle point, hopefully the previous iteration's velocity or the momentum is going to carry it forward into the next one. And we saw that before. So this kind of visualization where you see the purple ball essentially is moving through the local minima because of that reason, where it is taking the previous iteration's velocity into consideration before moving on to the global minima. But sometimes this is insufficient by itself, momentum itself, because when we look back at it, what we are changing here is the way we are calculating the gradients, but alpha still remains the same. If you go back to when we were showing like regression, alpha is something that is very important, right? Even very much back in homework number 2, you had a question that showed you how learning rate in fact affected your optimization process. So alpha is not just a simple constant where you just set it up in the beginning and leave it. It's something that needs to change over time. So there are some algorithms that do this. These are adaptive learning algorithms that change your alpha over over time. The first one that we saw was this adagrad function. Essentially what it was doing is it was dividing alpha given some kind of a function that is based on existing gradients. So it accumulates all your previous gradients as the square of those gradients. So g of t plus 1 is g of t plus dou L by dou W whole square. So from the first iteration, you'll start off by g of 0 is equal to 0. You don't have any accumulated gradient at the time, but after the first iteration, you'll start accumulating gradients and use that in order to decay your learning rate. Alpha becomes lesser and lesser compared to like having a fixed constant based on the fact that you'll have some g of t plus 1 and some epsilon, so that it doesn't become infinity. So g of t plus 1 is a historical sum of squares in each dimension. So essentially, if you have more features, you'll need to have more gradients across those features. This was this kind of a demo that we saw, the difference between how adagrad would be versus gradient descent. Again, it's more easily able to move across the saddle point because of the fact that it has an accumulated set of gradients before, which it's using to change its alpha parameters. If it's not moving much, then that means that the gradient is very low and you're adapting your rate, essentially, and the opposite happens in adagrad. But sometimes what the problem with adagrad is the first iteration is very good. Adagrad works quite well because you start off with an accumulated gradient of 0, and then you have a similar gradient, you have a similar size as the gradient descent. But sometimes your gradients can be very large. You might have noticed this. Anytime you have optimized, if you just print out the first norm of your gradients, you'll notice that it's very high in the beginning and keeps on going lower down the later. So if your gradient is very high from the second iteration, your movement is very less. Alpha divided by a very large number will give you a very small multiplicand, right? So if alpha is, let's say, 1 and your denominator is very high, this will be almost 0. So Wt plus 1 will almost be equal to Wt. So there's no movement at all after the second iteration onwards because your g of t plus 1 can be extremely high to start off with. So to make sure that that does not happen, RMS prop adds this kind of a beta parameter, which is a weighted average of gradients. So this beta is a decay factor for the g of t plus 1. So beta of g of t plus 1 minus beta, in order to cancel it out, dou L by dou W whole square. And we saw this kind of a visualization where the green one is RMS prop and the white ball here represents adagrad. So you can see that in the beginning, adagrad moves along with RMS prop, but after a while it stops. It's not moving at all. And the size of these squares here that you saw before is essentially the amount of squared gradient that you have in each dimension. So this is just a very simple 2D graph. So your white ball here, even from the second iteration onwards, will have a very large set of gradients. And it's not able to move away from it because, again, it has a historical set of gradients that it's using, and it's not able to move past it. But the green ball, which is RMS prop, is able to go towards the minimum. So this is where we had stopped, I believe, on Wednesday with RMS prop, but I think I'd gone very fast in these slides, so I just wanted to bring them back this time as well. The next one, and possibly right now the one that is used the most in terms of optimization, is ADAM. ADAM is adaptive moment estimation, and it's kind of a combination of two things, the momentum part and the RMS prop. So if I go back to momentum, right, what we changed was the V of t plus 1. So let me actually go back there and show you that Wt plus 1 was equal to Wt minus alpha Vt plus 1. So instead of doing it on the gradient, dou L by dou W, we did it on the momentum, which was V of t plus 1, or we changed the momentum. Instead of the gradient, we used momentum here, but alpha remained the same. In adagrad and RMS prop, what changed was the alpha. We decayed alpha based on some historical set of gradients that we had before. ADAM combines these two things, where it does this kind of the bottom one here is Adam. So it's changing the dou L by dou W to V of t plus 1, which is from momentum, and it's decaying the learning rate as well. Alpha is not just alpha anymore, rather it's alpha divided by some factor, which is given by the RMS prop that we had before. So the beta parameter is the same decay parameter that had existed before, but now it's beta 1 for V of t plus 1 and beta 2 for G of t plus 1. So this motivation is very important rather than the math part itself, because we are more in, so again, this is more of a fundamentals course. If this were an optimization course, we would have spent the entire lecture just talking about Adam, just talking about RMS prop and so on. So it's very important. Just the motivation part is more important for us right now. There's a lot of math that has gone into trying to decide what the best beta 1 and beta 2 parameters are. Currently, the best accepted ones are that the beta 2 parameter, which is an accumulated set of gradients, has to be very, very close to 1. So it's something like 0.99. And beta 1 parameter also should be close to 1, but has to be less than beta 2. And we usually take it as 0.9. Again, there's a lot of mathematical reasons for deriving these things, but we're not going into the exact definitions of beta 1 and beta 2. The most important reason for that is something called bias correction. So bias correction is something that is required in the first few iterations, similar to what was happening with RMS prop and Adagrad. Same thing now happens here with Adam as well, because we have a momentum V of t plus 1 that is looking at the previous set of gradients, and we have alpha parameter that is being decayed by G of t plus 1. So in the first few iterations, your estimates might be very much biased when you're using Adam. So in order to correct for that, we have a 1 minus beta 2 t and a 1 minus beta 1 t that we use in the framework. Again, the math of this is not as important for us. It's just the motivation for what we are doing is important. And this bias correction is very similar to what we did between RMS prop and Adagrad. So, sorry, my PowerPoint closed. All right, not sure why. Any questions about Adam itself, the motivations for Adam? Question? So bias is essentially when we have this beta 2 and beta 1 term, what happens is that in the beginning stages, your gradients might not be high enough. So what happens then is that your beta 1 and beta 2 are controlling the entire optimization framework themselves without actually looking at the data itself or the gradient itself. In order to reduce that, we are doing this kind of an unbiased estimation for your update weights itself, which we call as the bias correction. Again, it is only relevant in the first few updates and in a few data sets. But in those kind of data sets, it can become a very limiting factor. So it's a very important part within Adam framework itself. Whenever we are dealing with more ImageNet-like data sets, it doesn't come into picture as much, but much smaller data sets, bias correction is very, very important. It's, again, because of the fact that you have beta 1 and beta 2, which will control the entire update in the initial stages of the optimization process. All right. Then we have the Newton's method, which is a second order optimization framework. This is something that we had seen before as well during regression. The idea is, and maybe I can show this slide first. Yeah, the idea in gradient descent when we are using gradients directly is that gradients form this kind of a tangent. So at every point, gradients create this tangent, and then they say that, okay, the minimum will exist, the zero will exist if I extend this tangent until the very end, and maybe this is where the least function is. This is how gradients basically operate in order to find your solution. They create this tangent at a particular point, and this point is the loss at whatever iteration. So W0 is giving a particular loss, and you draw a tangent across it in order to find what your optimal set of parameters is going to be. But as you can see, in many cases, it's not optimal. We can't keep drawing these tangents, and maybe there is a better way of trying to estimate our results, right? Because we know that our curve itself is not a straight linear line, but rather it's curving somewhere, and its resultant is going to be somewhere here, the minimum point. And this is where we use the topography of the function itself in order to calculate the optimal set of points. In other words, we need the Hessian matrix, and once we have that Hessian matrix, we can create, instead of a linear line, we can create this kind of a curve. This is an approximation of the loss itself in the second degree. Now, the function that we are using here is very simple. It's a parabolic function, which means that a Hessian, and when we are using the second order representation, it's actually entirely accurate. Within a single iteration, we'll be able to get to the minimum, because we have the exact this kind of topography of the loss itself, and since it's a second order one, we'll be able to get to the minimum, right? So this is what Newton's method helps us to do. But in general, in CNNs at least, our loss landscape is something like this. It's non-convex. There's no single global minima, which is the same as local minima. It'll have some concave paths here as well, and multiple local minima. So the one that I'm drawing here is a local minima. So it's really hard to essentially use something like Newton's method in order to calculate your results. But if you were to calculate it, the most important thing that you need is this Hessian matrix. Instead of a single gradient, which is a first order gradient, we'll have this kind of a two-dimensional, multi-dimensional matrix, which is delta theta 1 square L of theta, and the next ones are going to be del square of theta 1 theta P L theta. So the second element here is going to be, second element is going to be del theta 1 theta 2 L of theta, delta theta 1 theta 3 L of theta, and the last one is going to be del theta 1 theta P L of theta. Of course, there's square over there as well because of the double differentiator. But this is the Hessian matrix that you're going to be using in order to calculate your Newton's method. Once you have this kind of a Hessian matrix, which we'll call a quadratic approximation, your output or the best set of parameters is going to be minus h of theta inverse del theta L theta. And this is going to be, sorry, not this. This is Newton's method. I think this is the one that should have been within the rectangle. Your next set of parameters in this next iteration, theta t plus 1, is given by theta t minus alpha. This part is same as gradient descent. Del theta L theta is also same as gradient descent. The difference here is that there's an additional term, h of theta inverse. So your Hessian matrix inverse is going to give you the best optimization, the best setup in a two-dimensional sense, in a second order sense. Your best set of parameters will be derived using this kind of equation. This is something that we saw during regression. Too much of this method itself, mainly because of one we have gone through, and more importantly, it's not something that is used. It's not something we can actually use within neural networks, because the amount of computation it requires is very expensive. Even in regression, we had mentioned that for a P cross P thing, it might be extremely expensive, right? So in this case, we have thousands and millions, we have billions of parameters, which essentially is extracting their features. So it's impossible for us to construct these matrices and take inverse of these matrices. So it's not something we can actually use in a normal framework within our deep learning framework. So what we have is approximations of the Hessian matrix itself, and that is basically BFGS and LBFGS algorithm. BFGS algorithm is that in the beginning, we start off with the Hessian matrix and then start taking the rank 1 approximation across these matrices. So when you did your singular value decomposition, you saw that a big matrix can be divided into 3 components, your U, S, and V. And you can store these 3 matrices separately. And when you're taking the inverse, it's the diagonal elements that you need to take the inverse, right? So you can take element by element. Sigma 1, you can take an inverse. Sigma 2, you can take an inverse, and then multiply everything. So theoretically, what you're doing is taking the h of theta inverse, but instead of doing it separately, instead of doing everything at once, what you're doing is a much more simpler way where you keep track of your U, your V, and your S, and your inverse is just going to be taking an inverse of these simple singular values. So again, it's a rank 1 approximation, so you've already seen that most of the time these approximations work in simple regression cases, but when you come to CNNs, it's not as simple. It's not, your rank 1 approximation might or might not work in such cases, but it's still a much easier way of taking inverse rather than taking h of theta and taking the inverse. In fact, it is something that we use. We can, limited memory BFGS is something we use in many cases when we are doing these kind of deep learning algorithms. LBFGS is something that we can implement, and we do implement. But the difference between BFGS and LBFGS is that it does not form or store the full inverse Hessian. You will do dimensionality reduction along with the rank 1 updates. You're taking only a smaller, you're basically compressing your algorithm, or you're basically compressing your matrix itself, Hessian matrix itself, and storing it and using it within the LBFGS algorithm rather than just doing a rank 1 update on top of it. So when you have a full batch, when you're trying to do this on a full batch of data points, LBFGS is your best bet in doing your solution. So you don't want to have like a batch gradient descent where you do 200 different epochs. In a much faster way, you can use LBFGS to get your solutions. So on small data, like let's say you have something like a 8x8 data, we'll see this when we talk about autoencoders. We can use LBFGS algorithm in order to optimize the framework. But of course, when you have much larger CNNs and larger images, in general, we usually use something like 224x224 as our image framework. That we cannot use any kind of an LBFGS or a BFGS algorithms. So just as a summary, we have talked about a lot of optimization algorithms, but depending on the loss landscape, your best bet is going to be ADAM. So without knowing anything about the data, without knowing anything about the algorithm, the network itself, the first thing that you should try is ADAM. But more you work on it, more you work on that particular data set and that particular network, you should probably then switch over to something like SGD with momentum. Your stochastic gradient descent with momentum still gives you the best results, but the difference is that you need to tune your learning rate more. So ADAM tunes it by itself, right? So we saw that it has a momentum factor and it has an alpha divided by something, which it decays it according to the epoch it is in. But SGD with momentum does not have that. It changes the gradient to the momentum or the velocity part, but the alpha part remains the same. So that is something that you need to tune. We have something called a learning rate scheduler that we usually use in deep learning algorithms, where we say that if we have 200 or 300 different epochs, the first few epochs will be, let's say, 0.1. After that, it will be some function of the epoch itself. Let's say it reduces to 0.01. First, let's say we have 200 epochs in total. First 60 epochs will be 0.1. Next 60 epochs will be 0.01. The ones after that is going to be 0.001. So on Cypher 10 dataset, the one that I just mentioned is very very commonly used. That learning rate scheduler with SGD and momentum will give you the best results. But again, it's very much dataset dependent and it's very much network dependent. So it's something that you would only use after you've worked with those exact specifications for a long time. But if you do, you can outperform Adam. You'll probably get the best results if you use SGD momentum and a good tuned learning rate. If full batch update is affordable, then LBFGS is probably your best bet. It's the best method. Again, there's many things that go into this. Full batch update would require that the size of your data is small. So anything, even CIFAR10 or MNIST, which is 28 cross 28, you won't be able to use LBFGS. But if it's something like a much smaller 8 cross 8 or 11 cross 11 image, then it's more easier. Or it's possible to use something like LBFGS within your optimization framework. We'll see that more during the when we talk about autoencoders. Now, the last few slides is a little bit of exercise. We won't go through this, and it will not be asked in either exams or the homeworks and stuff like that. But it's just there for you to go through. There's a lot of papers here as well that has been linked. So whenever we talk about GoogleNet, for instance, we talked about the version 1 that was called InceptionNet v1. But since then, a number of other things have also happened. There's, I believe, InceptionNet v3, which back in 2017 or 2018 got the highest or the best results on ImageNet dataset. So there's a lot of new things that happen on top of these networks. So again, we concentrated only on the pivotal architectures, but on top of that, other things have also happened. So this slide tries to go through and gives you resources. So if you are interested, it's a very good idea to just go through some of these exercises just to get an idea basically of how to use something like PyTorch and create architectures for yourself. You can take the original AlexNet and make some changes about the batch size, and same thing with BGG as well. You can compare it with AlexNet and changing the height dimensions. I think GoogleNet has the most amount of changes that has been made. So when InceptionNet v1 came out back in 2014 versus now, the differences that have existed is quite a lot. So you can use multiple things with each other. So for instance, even though we describe residual connection, the skip connection with respect to ResNet, you can use that within the InceptionNet framework as well. So there's a lot of innovation that has happened on top of the pivotal architectures for your for getting better results essentially. Same thing with ResNet as well. Again, in 2016, it was the first one that beat the human benchmark in terms of the error rate, but since then it has become better and better. I do want to say one thing about the results themselves. Even though it exceeded the human benchmark, it kind of has overfit to the ImageNet dataset itself. So ImageNet dataset was kind of derived from Flickr dataset, where all the data, all the images are pretty high quality. So it's user-generated images that was uploaded online. So what that means is that most people who upload it online are going to upload good-looking images. So it's very high-quality images of people, of objects or animals, let's say. So anything that is of lower quality, let's say any kind of a motion blur or some kind of a noise, if that exists within the images, it's still very bad. Your deep neural networks are very bad in terms of classification. There's a lot of robustness approaches that have been developed, but even till today, it's you train it with, let's say, Gaussian noise, and then you put in Gaussian blur, your network is not going to do well. During training, if you have Gaussian noise, and during testing, if you have Gaussian blur, it's not able to generalize between these two noise categories very well. And that is a major challenge currently with deep networks. The robustness of these algorithms, it's very much overfit to the data set, the training data that it was learned on. So the test distributions, if they are the same, then well and good. You perform better than humans. But as soon as that changes a little bit, it's quite problematic. That's it for today. So the goal was just to complete what we were not able to do on last Wednesday. Best of luck for your exam on Wednesday. I'll be here right now if anybody has any questions. Otherwise, of course, I'll be in office hours as well.